Okay, let's take a look at the following problem. You have a charge here in the corner of a cube, and we are to calculate the flow through the surface S, this one here. And that is defined, the electric flow is defined like this integral, electric field dot product with the surface element dA, which has a direction, a normal direction outward from the surface. Okay, so let's calculate that. So we know from Coulomb's law that this is the electric field, and that basis unit vector can be rewritten like the r vector divided by the distance r. So the electric field can be written like this. And then we look at this r vector on the surface. And then look at the coordinate system, x, y, z. And the cube length is L, capital L. So the y value on the surface is always L. And then x is varying like that, and also z. So here is the vector on the surface. And the surface element, it is going like in this direction, dx, and then the z. And as I said, the direction of this element is outward. Can you see that? In the y direction. That's why we have dx, dz, and then the y direction unit basis vector. So let's, when we want to do this dot product here, so obviously it's going to involve the position vector r. So let's look at this, r dot dA. And then, okay, this times the x component, there is no one here, right? It's the y only. So, okay, L times the y component, yeah, that's what you have here. And then C times the C component, but you don't have any. So that's 0. So all you get from the dot product is this thing here. And now we can set up the flow. So this is a constant, q over 4 pi e naught. So we break out from the integral. And so it's this guy here, and that's got dot product with dA, but that we just calculated to this L dx dc. And then the r cubed is still here within the integral, because when you're integrating, this is the r distance is varying. So it's not the constant, because this distance from that, sometimes it's a certain distance and sometimes it's a different distance. Okay, but L here is a constant, so we break that out. It's here. And then, okay, so r, what is the distance? Here, that's the square of that, square of that, square of that, sum them and square root. And then you have the power of 3 or the square root, so then it's 3/2 here. So this is 1 over r3, and then the dx dc. So with the double integral, we can first integrate this guy here with respect to x. So we take that guy. And when we integrate that, then everything except x can be seen as a constant. So L and C is treated as a constant, and x is the one who is the variable. And you can look up in the integral tables what this type of integral is, x squared plus constant. And this is what you find as primitive function, and then L, yeah, here minus and then 0. So it's only that one. So we already fixed the first integral here, and then the second integral. So QL 4p pi e naught, and then L, break out that. So you have now QL squared, this, and that guy is over here. And then that guy is over there. So a final integral to compute. And yeah, again, you can look in a mathematical handbook or something. And what you find is pi over 6L squared. And here's the final result. So this is the flow through that surface. But we could have solved this by using symmetry instead. So look here, here is the charge, and here is the surface we just calculated, the flow through that surface. But by symmetry, that is the same as the flow through this surface actually. Or that surface, or that surface, all the surfaces you see here, is it would be the same flow. And how many surfaces do we have? 1, 2, 3, 4, 5, 6, 7, 8. Going around like that. Then 1, 2, 3, 4 outer surfaces towards us. So it's 8 surfaces, and then you need to place another 4 cubes behind the charge. So 8 plus 4, 12 surfaces, and then behind the charge another 12 surfaces, i.e. 24 surfaces. And then you can use this, the flow through a closed surface. So we treat all those surfaces that we have 8 cubes, and then the exterior surfaces is seen as one surface. So the total flow through that is Q over E naught. But this guy here is just 1 of 24 such surfaces. 8 around plus 4, that's 12, and another 4 cubes behind the charge. So 24 such surfaces. So it should be only 1 24th of Q over E naught. So through symmetry, we could solve this immediately, basically.